So I want to continue where we left off last time, and what I really should have put on last time, but I knew the last video was getting kind of long, so I left it off, was Theorem 4, which I'm going to call the prime number theorem. And you might see other things called the prime number theorem, but what we can say is for any real number x, the number of primes less than or equal to x is big theta of x over natural log x. And I just want you to think of this as an estimate for roughly how many primes we have. So if I say x is 1,000,000, we've got roughly 1,000,000 over natural log 1,000,000 primes. And so this theta means bounded above and below by constants. It's not so important that you see. It's not so important that you see this as. And actually, I'm gonna specify any x positive. Natural log of a negative number doesn't make sense for any x positive. But it's more just an estimate of how many primes there are. It doesn't exactly tell us how many primes there are because this is big theta. We're bounded above and below by a constant, but roughly how many primes there are. So what I want to do now is move on to the next section or subsection of this section, and that is going to be with GCDs. So given any two integers, but we're mostly going to be using natural numbers, a and b, the largest integer that divides them both is called their greatest common divisor. And we often denote it GCD of A and B, but sometimes you'll see it as just A and B in parentheses. Okay, I don't like this notation because I think there are a number of things that are A comma B. I mean, from inner products to open intervals or coordinates, there are just a number of things. So I'm going to try to avoid that notation, but I'm just letting you know in case you find it online. If GCD of A and B is equal to 1, then we say A and B are coprime, or alternatively, but equally, relatively prime. So the terms coprime and relatively prime mean the same thing. The smallest natural number that is a multiple of both A and B is called their least common multiple, written LCM AB. So this, you've probably seen the least common multiple when you're trying to add fractions. You're looking for the lowest common denominator, or least common denominator. That's going to be the least common multiple of your two denominators. Well, let's do a quick theorem that sort of fleshes this out a little bit. And you don't need to know the proof of this. I'm not even going to give you the proof of this. I'm just going to state it. So given A and B natural numbers, and like I said, we're mostly going to be working with natural numbers here, we have that the GCD of A and B times the LCM of A and B is equal to A times B. And I don't want to prove this, but I want to kind of just demonstrate an example of it working. So let's look at 24 times 36. So 24 times 36 happens to be the same thing. Well, let me break everything down. This is going to be 2 cubed times 3, and 36 is going to be 2 squared times 3 squared. So if we remember how to find the GCD, the greatest common divisor is going to be, what happens when we look at all the factors that are in both. The greatest common divisor then is going to be 2 squared times 3. And the least common multiple is going to be kind of everything else. So it's going to be 2 cubed times 3 squared. So that's everything. It's got to have at least enough to cover each factor. And we notice this is precisely the GCD of A and B, and this is the LCM of A and B. I think I would do more with this, but I just want you to think of this as a rearrangement of factors if we were looking at just sets, but keeping track of how many times each element in the set repeated. Now that's not how we do sets in this class, but there is something similar called a multiset, and this is kind of like managing the multisets of the factors. This works because we have unique factorizations, right? That no matter what my number is, its sort of DNA of primes is always unique. So this is kind of looking forward to a more combinatorial theorem we'll see later, but I just kind of wanted to show this to you. Okay, so the sort of the big fish for this video is going to be the Euclidean algorithm. So I'll just describe it. The Euclidean algorithm is a process for finding the GCD of two numbers by repeatedly applying the division algorithm. Okay, so we're going to keep taking the division algorithm and applying it over and over and over again. So I'm going to set this up in 2 columns where I'm going to give you the general Euclidean algorithm, and then I'll do an example so you can kind of see what's happening on each, both in general as well as in the precise example. So in general, and then a concrete example. Because I think it's just kind of a waste of time for me to describe this in general too much without giving you a concrete example. I want you to be able to see them side by side. So in general, I'm going to start with A equals Q1B plus R1. So I've applied the division algorithm to A and B. And then what I'm going to do is I'm going to shift this number over to here, and I'm going to shift this number over to here, and I'm going to get B is equal to Q2 times R1 plus R2. So, the new things here are Q1 and R1. The new things here are Q2 and R2. Right, and then I'm going to shift this over. I'm going to say R1 is equal to, well, there's a new thing, Q3 R2, shifted over, plus R3. So new, again, Q3 and R3. And we keep doing this, keep doing this, keep doing this until we get to the stage R sub k minus 2 equals Q sub k, R sub k minus 1 plus R sub k. So the new thing here was R sub k and Q sub k. And then at the next, so how do we know we're at the kth stage? Well, it depends on what the next stage is, and that's R sub k minus 1 equals Q sub k plus 1, R sub k plus 0. So we keep shifting things over and doing the division algorithm until we get to the point where there is no remainder. And when we, whoa, that's weird. When we get to the point where there's no remainder, that means that this was our GCD. Okay? So let me give you a concrete example, because I don't think that makes a whole lot of sense. So I don't want to spend a whole lot of time describing that. I want you to see it so that when we do the concrete example, you can look back at it. So let's do the following concrete example. Let's find the GCD. So this is just the GCD of two natural numbers, a and b. You can actually do two integers, but I'm going to just do this for natural numbers. Let's do a concrete example, finding the GCD of 287 and 91. And I like to put the bigger number on the left. We'll see. So I'm going to write 287 equals something times 91 plus something else, where I apply the division algorithm. So let's apply the division algorithm. How many times does 91 go into 287? Let's just figure it out. So 91 goes on the outside of the house, 287 goes on the inside of the house. How many times does 9 go into 28? It goes in there 3 times. So 3 times 1 is 3, 3 times 9 is 27. Subtract 287 from 273, and my remainder is 14. So the answer here is 287 equals 3 times 91 plus 14. And these Q factors are always going to get shifted away. The main thing I'm concerned about at each stage is the new remainder. Okay, so now I shift 91 over, and my next stage is 91 equals something times 14 plus something else. Okay, how many times does 14 go into 91? Well, I think it's about 6, because 15 goes into 90 6 times, but let's just work it out. How many times does 14 go into 91? Well, it goes in there 6 times. 6 times 4 is 24. And so 6 times 1 is 8 plus 2, it's 84. And what's left over? Well, there's a remainder of 7. Okay, so my remainder is 7. And this number actually doesn't matter for this calculation, but it will matter for some other calculations we're going to do later. So then on my next stage, I say 14 is equal to something times 7 plus something. Well, hopefully everyone watching this can do this in their heads. 14 is equal to 2 times 7 plus 0. Now we've reached 0, which means this number right here is the GCD. So the GCD of 287 and 91 is equal to 7. That's because when I get to 0, it's the previous remainder. Okay, and some of you might say, oh, when you get to 0, it's just the last number you wrote down. That's fine. I like to think of it this way because I like to think of it as whatever happened at stage K. So I recommend that you go through and do a bunch of examples of that if you can. The next thing I want to do is I want to talk about the Bezu identity, and I'm going to do that down here, and then I'll use, sorry, well, I guess I should connect this back. So you see I started with A and B, so A and B, and then I found Q1 and R1 using the division algorithm. Then I shifted this number over and this number over. See, I shifted B over, I shifted the new remainder over. And then I just kept repeating that process. This number keeps sliding over, see? And you keep doing that until you get to this 0, and when you get to this 0, ding, 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 the last remainder before 0 is your GCD. So let me tell you the Bezu identity, and this is Theorem 6, and I'm going to kind of smash it in down here because I don't think the theorem is so important for us as the process that we're going to be using, the Bezu identity. And this is given any two integers, a and b, and again, we're going to be using mostly natural numbers. There exist integers, s and t, integers, such that SA plus TB equals the GCD of A and B. Now, this is important because, if I have if I have an integer linear combination, I might not be able to get certain numbers out. And let me give you an example, just a quick example of where this doesn't apply. I can't write an odd number as a sum of s times even plus t times even for any s and t integers, right? No matter how many times I add or subtract even numbers, whole multiples of even numbers, I can't get an odd number out. And that's because any pair of even numbers that I look at, their GCD is greater than 1. Their GCD is at least 2. So the point here is that this Theorem 6 says I can get down to the GCD. So if I've got two numbers and I've computed their GCD, then there exists an integer linear combination. That is something that looks like this SA plus TB. You're going to hear me call this an integer linear combination. There exists an integer linear combination that gives me their GCD. So what I want to do is I want to take a concrete example, and I want to now do the Bezu identity for the GCD of 287 and 91. So that is, I'm looking for integers s and t such that 287 times s plus 91 times t is equal to 7, because we found their GCD was 7. Now, when we're doing this, I'm typically going to give you natural numbers for a and b, which means one of these is going to be a positive integer and one of these is going to be a negative integer. So since these are both positive, we're going to have typically one of these positive and one of these negative. So here we are going to have integers. And the way we're going to do this is we're going to just run through the Euclidean algorithm backwards. So what I'm going to do is I'm going to solve this for 7. Okay, I do this by running through the Euclidean algorithm. So that's why I need to write down all these numbers from this calculation. Run through the Euclidean algorithm backwards, and we start by solving for, or writing everything in terms of the other thing, so I'm going to say solving for the GCD. That is, I'm going to write the GCD in terms of everything else. So I'm going to solve this equation in terms of 7. I'm going to solve this equation for 7 in terms of the other numbers. So I'm going to write this as 7 equals 91 minus 6 times 14. And then I'm going to do what I call Scooby-Dooing, okay? Because I've got this 14 here, and 14 isn't 91 or 287, right? So 14, though, I can write as an integer linear combination of 91 and 287. So it's just like the end of Scooby-Doo when, they're like, wait, who was the haunted ghost pirate? It wasn't a haunted ghost pirate. They pull off the mask and it was really, Old Man Withers from the amusement park. So I'm going to say 7 is equal to 91 minus 6 times, well, who was 14 really? Well, I look at this. 14 was really 287 minus 3 times 91. So that's my Scooby-Dooing. And then I simplify. So now I'm going to write this as something times 91 plus something times 287. So 7 equals, how many 91s do I have? I've got a 91 here, and then I've got negative 6 times negative 3. Well, negative 6 times negative 3 is 18. So here I've got 18 91s, and here I've got another one. So this is 19 times 91. And how many 287s do I have? I've got negative 6 copies of 287. So minus 6 times 287. Okay, now I get to the end here. Here is my Bezu identity, right? So in this case, my S was equal to negative 6, and my T was equal to 19. But what I can do is I can actually check whether or not this is right. So let's zoom in here. What's 19 times 91? Well, 9 times 1 is 9. 9 times 9 is 81. And then I've got 1 times this, so 9, 10. So 9, 2, so 1729. So this number is 1729, right there. And what is 6 times 287? 287 times 6. Well, 6 times 7 is 42, carry the 4. 6 times 8 is 48. 8 plus 4, so that's going to be 2, carry 5. 6 times 2 is 12 plus 5 is 1722. So this is 1722. And guess what? 1729 minus 1722 is indeed 7. So I not only found an integer linear combination, but I also checked that it was correct. So this is the Bezu identity. And I'm going to cut the video here because the next set of results kind of fit